Hello once again. So in my pre-calculus classes, we're going to start talking about the inverse trig functions, the arcsine, arccosine, arctangent things. And I thought it'd be a good idea to preview that with some things from Algebra 2, as far as what does it mean to take an inverse? How do we know how to find an inverse algebraically? And what does it mean graphically? Um, and all that good stuff like that. So I'm going to go through a couple of these things as we do that. So I'm going to ask you to take a look at these questions and pause the video for just a minute and think of your Algebra 2 class and what you remember, and see if you can answer these questions for me. So pause the video and see if you know the answer to these things. So how do we find an inverse of a function? How do we graph it? And how do you know if the inverse itself is going to be a function? And if you remember, like the vertical line test, that's kind of what we're talking about there. So let's talk about the first one here. How do you find the inverse of a function algebraically? Hopefully you remember that from Algebra 2, but here there's two steps, only two steps. You switch the x and y values, literally switch them, and then you solve it for y. Using your algebra skills, doing the opposite operation, watching your signs, all that good stuff like that. So I've got just a couple of real quick examples that I want to take care of with you here. And again, if you want to pause the video just real fast and find the inverses of those two things, that would certainly be a good idea. But I'm going to go on here. I'll give you a couple seconds if you want to pause that. So what do we mean by switching the x and y values? Well, anytime you see f of x, we know that's really y. So we can rewrite that as y equals 2/3 x minus 5. Switch them literally means switch places. And then use your algebra skills to get y by itself. So we'd add 5 to both sides. And from there, we would multiply by the reciprocal. We want to get y by itself, so 3/2 on both sides. And in the interest of time, I'm going to leave it like that. 3/2 times x plus 5 would be equal to y, and we notate that with a little -1. That's not an exponent. It doesn't mean y to the -1 power. That means the inverse of y is this function, 3/2 times x plus 5. We could certainly distribute that through, and that'd be a different form of that, but it would be the same function. We're going to do the exact same thing for this guy over here. So we are going to switch the x and y's. I'm going to go and skip the first step. So we'd have x equals 3y squared plus 1. Subtract 1 from both sides. So we have x minus 1 equals 3y squared divided by 3. So we want to get the variable by itself. So we have x minus 1 all over 3. Important that we have that as a whole term, equals y squared. How do you get rid of the y squared? Again, always do the opposite, so we got to do the square root of both sides. And in this case, it is important that we have the plus or minus. So the actual inverse of y is going to be plus or minus the square root of the whole quantity x minus 1 divided by 3. So that's all well and good, and the algebra certainly is important that we can do that by hand, but what would that look like graphically? So again, think for a minute back from Algebra 2 and see if you can kind of visualize. I'm going to show you kind of a calculator screenshot, but see if you can visualize what the graphs of the function and its inverse would look like and kind of what the properties of that would be. So that first, the linear function that we did, here is what that would look like if you graph that. In blue is the original function, and then in red is the inverse. What do you notice about those two things? Are they both functions? Is there any kind of symmetry that we can talk about between those two lines? And then the same questions. Here's the two graphs from the quadratic, 3x squared plus 1, again in blue. And then the plus or minus, I had to kind of do two separate equations to get it graphed correctly. The plus or minus is there in red, plus or minus root x minus 1 over 3. And again, ask yourself the same questions. Are both of those functions? And what is the relationship between those two functions? Well, whether you notice it just when you see the graphs, or if you remember from algebra 1, remember graphically, it means that these functions are symmetric about the line y equals x. And it's the same thing for both of them. Anytime you take an inverse, the two graphs are symmetric about the line y equals x, which is what, if you think about it, algebraically, when we switch y and x, that's what it means graphically. We're literally switching the x and y coordinates. Okay, so if you notice, it's an easy one to notice kind of on the quadratic. If you look at this point right here, this point would be 0, 1 on the original graph, whereas on the inverse graph, that point is 1, 0. So you switch the x and y values, whether you're doing graphically or algebraically, and that is where you get the inverse function. Okay, but I do hope you notice, so on the linear function, obviously the inverse of a linear function is also a linear function, so it passed the vertical line test. But over here on the quadratic, the inverse of this is your sideways parabola, and that's obviously not a function. That red graph there does not pass the vertical line test. So is there some kind of generalization that we can make that how could we know, just by looking at an equation or function, how could we know that the inverse would also be a function? And again, if you want to pause the video for just 1 second and think about that, can we make that general statement about when the inverse would also be a function? Well, what happens is a function is what we call invertible, and the inverse will itself be a function when it's 1-to-1. What does a 1-to-1 function mean? Basically, it means it's always going to go up or always going to go down through the entire domain across all real numbers. Graphically, it means it also passes what's called the horizontal line test. So if I go back and take a look at these guys again, let me get rid of these guys. Obviously, the initial parabola, 3x squared plus 1, that does not pass the horizontal line test. So that's why my inverse is not a function. But if you look at the linear function, that does pass the horizontal line test. So your inverse is going to be a function. Okay? So we're looking for a function that is going to pass the horizontal line test in order for its inverse to also be a function, something we can use kind of in application-wise. So my last question about these two here, before you actually get into the trig functions, is how could we make this function, the function in blue, 3x squared plus 1, how could we manipulate, not manipulate that, but how could we think of that function to where it would be 1-to-1? And I want you to think about that for a second. Again, pause the video for just 1 second. How could we maybe change how we view that function to make that 3x squared graph 1-to-1 so that the inverse would be a function? Well, what if we chop it off? What if we literally kind of chop it off from here and ignore that side of it? So we're going to restrict the domain just from 0 to infinity. What would that do to the inverse? Well, it would also chop off this back end over here, because now we're not worried about the negative end of it. All we care about is the positive x values. So to clean that up a little bit, it'll look like this. And that would be an invertible function where both of them are now functions. So this is x squared, just as the domain goes from 0 to infinity. And this is the inverse of that, square root of x. You might remember that from your parent functions, where the domain now is from 1 to infinity. So those are your those are your inverse functions for that. And again, we can restrict the domain any way we want to, as long as it's 1-to-1, because that means then the inverse of the function will then itself be also a function. So what does that mean for our sine, cosine, tangent functions? If you can think of, for a minute, just what those parent functions look like. So here is your sine, cosine, tangent functions. Think about those for a second. Are they one-to-one? I think it's pretty clear that they're not. They do not pass the horizontal line test. But also, you know, the next step of that, just like we did with the quadratic, how can we look at that function and restrict the domain to where it is one-to-one? Where could we kind of chop those graphs off to only think about a part of it to where it's always increasing or always decreasing around some kind of easy numbers that we're familiar with? Well, for the sine function, what if we chop it off right here as the beginning point and then end it right here? So we just have this little spot right here, and you see that from there to there, it is always increasing. How about for cosine? Well, here, what if we just started at x equals 0 and we end it here? That would be x equals pi. And again, from here to here, you see that the graph is always decreasing. By the way, I should have said this a moment ago on the sine graph. Notice these two functions from the minimum value to the maximum value, that goes from negative pi over 2 to positive pi over 2. So if we restrict that domain from negative pi over 2 to pi over 2, we have a one-to-one function. If we restrict cosine from 0 to pi, we have a one-to-one function. And the same thing for tangent. If we restrict the domain to just that one cycle, again, between negative pi over 2 and positive pi over 2, all of a sudden we have a graph that is one-to-one, always increasing on that restricted domain. So now all of a sudden we can talk about the graph of the inverse and what that is going to look like. So that's the last thing I'm going to talk about. So here is your notation, and what I want you to know when you come in and we start talking about the inverse trig function. So sine minus 1, again, that's this notation that means the inverse sine. You'll also see it written as arc sine, and this is the graph. And I want you to know that the domain of this graph, notice the domain from negative pi over 2 to pi over 2. I'm sorry, the domain negative 1 to 1, because we're reversing everything. So remember, the range of the parent function was negative 1 to 1, so my domain of my arc sine is going to be from negative 1 to 1, and then the range, and here's going to be the important part, as we're going to talk about in class, the range will be from negative pi over 2 to pi over 2. Because again, that was the domain of the parent function that we restricted, and that'll become the range of our inverse function. Okay? Same thing for the inverse cosine function, or the arc cosine function as it's called. The domain here is going to be from negative 1 to 1 again, because we know cosine and sine values both always have to be between negative 1 and 1. And the range here, notice that we restricted the range here a little bit differently on the parent function. Now we're going to go as our range here from 0 to pi as the range. And then lastly, we'll go to the arctangent function. Again, the same kind of notation. The domain here is all real numbers. Because remember, tangent can be anything because it's asymptotic, and we can go kind of all over the place for the range. But again, that switches down to the domain. And the range for the arctangent, just like arc sine, will go from negative pi over 2 to pi over 2. Okay? So jot those down. Feel free to kind of go back and take a look at those again. But we are going to be using these kind of things, particularly looking at composition functions and kind of going using the unit circle again to talk about the domain and range and evaluating the arc sine, arccosine, and arctangent functions moving forward. I appreciate your time. I hope you got something out of this, and we will discuss this more in class. Um, I'll link to some videos about graphing these things, and there'll be a video coming up shortly also about how to actually evaluate these things on your own and some composition function like that. Thank you again for watching. We will see you next time.